Welcome back, students. Today we're going to be talking about analyzing lines of fit, and we're even going to go into finding the line of best fit. All right, so first we're going to talk about one way that we can tell whether or not a model actually fits the data well, and it's going to be through analyzing the residuals. Now, whenever we drew one of our trend lines, not all the points would be exactly on the trend line. Some would be a bit off. So, for example, this data point right here appears to be 3 places away from the line. Now, that is going to be a residual of +3. This data point is 2 places below, so that residual is going to be a -2. Now, as we begin creating these trend lines, if we make a graph of the residuals, what we're looking for is that the residuals seem to be scattered and don't seem to have a pattern to them. If our residuals do seem to be scattered and don't seem to have a pattern, then great, the model you made works well. If, however, when you graph all your residuals, there seems to be a pattern there, that would indicate that our line that we drew is actually not a good match for it. And as time goes on, our line is going to get further and further away from what the actual model should have been. All right, so let's go ahead and look at this example. Now, this is actually the equation that we generated in the last notes, that the sales were going down by 2 million, but that the opening week sales were around 20 million. And we're going to put it to this data and analyze, was our equation actually a good fit for that model? All right, so let's go ahead and first figure out how far away our actual sales were from the predicted sales, the sales that our equation would have predicted. So let's see, -2 times 1 will be -2. -2 plus a 20 is an 18. All right, and then -2 times 2 would be a 4. -4 plus 20 is a 16. And in fact, because of this slope of -2, it's just going to go down 2 each time. So no need to make this any harder than it needs to be. All right, so next, our residuals are going to come from subtracting the actual predicted point from what we had. So I'm going to take so we're going to take the actual point and subtract the predicted point. So 19 minus 18, we have a residual of 1. 15 minus 16, that's a -1. 13 minus 14, -1. 11 minus 12, -1. 10 minus 10 is a 0. 0, 1, 1. All right, so let's go ahead and look at that. At 1, so now I'm using my weeks and my residuals for the graph. Okay, so when x was a 1, our residual was a 1. When x was a 2, our residual was a -1. Then we had another -1, -1, a 0, a 0, and a 1 and a 1. All right, so there we have it for our residual plot. I do think I see a bit of an up-down pattern happening to these residuals. So I'm a bit suspicious of this model being a good fit for the data because of this pattern that I'm seeing in residuals. Now notice, if this pattern were to continue, we would predict that our residuals are going to get bigger and bigger and bigger, meaning our line is getting further and further away, which would make sense in the future. Think about what's going to happen according to our prediction. The sales are going to continue to go down by 2 million. Well, eventually we'd be in the negatives, but that doesn't make any sense. You can't have negative sales, and it's not just going to continue in forever. So our model probably isn't a good fit. All right, let's go to this next one. So we've got people's ages and their salaries. And it looks like your salary goes up by 0.2. I'm going to guess that this was talking in terms of 1,000, so 42,000 a year, 44,000 a year. So that would be saying that this is going up by $200 every year with a starting average salary of about 38,000 is what that equation would be saying. So let's go ahead and find our residuals, see if this actually is a good predictor of how your salary is going to increase and how we could predict people's salaries based off of their ages. All right, so first at age 35, so we need to do 35 times 0.2, which should be about a 7, and a 7 plus 38 is going to become 45, and then the 42 minus 45 is going to be -3. All right, so I'm going to quickly pause the video and get the rest of this filled in. Just remember, I'm using this equation with these numbers for x. So I had done 0.2 times 35 plus 38 equals this. All right, so now to find my residuals, I just need to do my subtraction. 44 minus 45.4 is going to give me -1.4. 47 minus 46.2 is a 0.8. And we'll have 3.4, 5, 3.6, 0.4, and -4. All right, so let's go ahead and graph it. In order to graph these, the ages will be x, the residuals will be y. So let's get those. At 35, we should be down at -3. At 37, at a -1.4. So these are going to be approximate. You're going to have to approximate where 37 is on there and where -1.4 is. Next, at 41, we should be at a 0.8. And then at a 43, at a 3.4. Okay, 45 would be at 5. 47 at 3.6. 53 at a 0.4. And a 55 at -4. Once again, I feel like I am seeing a pattern emerging from those dots. And I gotta say, I don't think this is going to be a good fit either. What we're looking for in residuals is a bit more of a scattered look to the dots. Now, I would definitely say that this residual plot above looks far better, looks more scattered than this one below. So the one above is probably a better fit than this one below would be. Now that's how to use these to be able to figure out, is my equation a good fit for this data? Now let's talk about another way to find out if it's a good fit, and it's called the correlation coefficient. A correlation coefficient is just a measurement of how strong the relationship is. How well do all the dots line up and follow whatever line we've created for our equation. They tend to explain how much of the variation can be explained through our model. Now this correlation coefficient goes from values of -1 to a +1. The closer you are to 0, the closer it is to saying there is no relationship there. So if your correlation coefficient is close to 0, that's no relationship. A correlation coefficient of either a +1 or a -1 means the dots line up exactly. Okay, there is no variation. They line up perfectly. That is a perfect correlation. So the closer you are to a 1 or a -1, the stronger the correlation is. The closer you are to 0, the weaker the correlation is. So we're going to go ahead and label a number line to talk about the strength of the correlation. All right, so I've got my number line labeled. Now, once again, at 1, it is a perfect correlation. It is exact. There is no variation from your model. Okay? The big difference is whether we call it positive or negative correlation. And that's the nice thing about this value as well. Whenever you're saying positive or negative correlation, if this is a negative number, you have a negative correlation. If it's a positive number, you have positive correlation. Now, anything in between a 0.7 and a 0.9, so going from about there to there, I am going to call that strong. So that section would be a strong positive correlation. The same goes for on that side. This would be strong but negative. It's a strong negative correlation. Next, from about a 0.4 to a 0.6, so somewhere in that range, we are going to call this moderate. All right, and same up there. So there, oops. So there's the moderate range. All right, next from about a 0.1 and up. So within this range, it's kind of weak. And anything in this section is, we're just going to say there's no correlation there. Okay? So that is how we're going to identify strong, moderate, weak, positive or negative correlation, is by finding this correlation coefficient. Most programs will use the variable R. in order to identify what the correlation coefficient is. All right, so over here we've got this table is showing the duration in minutes of several eruptions from the geyser Old Faithful and the times in minutes until the next eruption. We're going to use a graphing calculator, Desmos, to find an equation for the line of best fit and then plot the data and the graph of this equation on the same viewing window. All right, then we're going to interpret our correlation coefficient. Okay, so first thing I need to do is to get all of those numbers put into a list in Desmos. So I'm going to give my list a name, A, then is equal to square brackets, or actually, sorry, because what we have here, sorry, one moment. Because what we have here is a table, I actually want to just insert a table. So click the plus sign, insert table, and now I'll type in all my x's. All right, now we'll insert the y's. Great. Now that I've got that all typed in, next I want to create my my y equals mx plus b regression. Now notice how in the table it labeled this as a y1 and an x1. I need to do the same thing as I create my equation. So I'm going to do y. Now to get the underscore of 1, you press shift and the minus key. Now I can press 1 and notice it gave me that underscore. I'm going to push forward so that I'm no longer in the underscore. Next, to the left of the number 1 on your keyboard, there is a squiggly sign. We want to put that in. So you press shift and then that key. And we've got our squiggly sign. Now the equation is usually m and then x. So, but our x, according to that table, was x1. So once again, shift, minus key, so we can name it x1 plus b. All right, so let's look at what this has done. It's graphed all those points. It has drawn the line over it, and looking at that line, it seems to be following those points pretty well. It has also told me what my slope and y-intercept are. The other nice thing that it's done is it's calculated R, my correlation coefficient, as a 0.97. All right, so let's just come right over here. We've done the graph. Now let's go ahead and interpret the correlation coefficient. Our correlation coefficient, R, was 0.98, which, according to what we drew above, that puts it in the strong positive range. So this is a strong positive correlation. Okay, the relationship between the duration of an eruption and when the next one is going to happen is a very strong relationship. Next, it wants us to interpret the slope and y-intercept of our line of best fit. So I'm going to go ahead and write my line of best fit. So we've got y is equal to, and then notice over here, our m is going to be 11.99. I'm going to go ahead and round that to 12. So y is equal to 12x plus, and b is about 35.1. So there's my mx plus b. Now we're ready to interpret it. First, the slope. The slope was a 12. I like to have it as a fraction, so we've got the y over x, so I'm just putting a 1 under it. The y values were time, and this was time in minutes. And more than that, let's see, y was the time in minutes until the next eruption. So this is 12 minutes until next. And then the x value was the duration. So that's 1 minute of eruption. So what this slope is telling me is that for every 1 minute Old Faithful is erupting, it'll be 12 more minutes until the next eruption. So if Old Faithful is erupting for 2 minutes, it'll be 24 minutes till the next eruption. If Old Faithful is erupting for 3 minutes, it'll be 36 minutes till the next eruption. That's kind of the way that slope increases it. Now that is not all of it. Just by virtue of it erupting, we also have this plus 35. So in all those things I just said, we should probably also add 35 minutes to it. So our y-intercept is kind of weird here because it's where your x is equal to 0. So we're saying if it erupted, but it erupted for no amount of time, so that's weird. That's not actually going to happen. But we're going to say with an eruption of 0 minutes, it will be 35 minutes till next. 35.1 minutes till the next eruption. And then we add on another 12 minutes for every 1 more minute that Old Faithful was erupting. All right. Now, we can use a graph, or we can use our equations to do what is called interpolation or extrapolation. An interpolation is when I make a prediction that is within the scope of the data I already have. So to take an example from what we see above, notice we have numbers that go from 2 to about a 4.2. So if I wanted to predict when Old Faithful is going to erupt again for, let's say, after watching it erupt for 3.5 minutes, that's going to create an interpolation. Okay, a prediction that is within those numbers. We never had anything above a 4.4 though. So if I saw Old Faithful erupt for 5 straight minutes and I wanted to predict when it's going to erupt again, that's outside of the scope that my current data has. So that would be extrapolation. So interpolation, it's inside my data. Extrapolation, it's outside the data that I already have. So let's go ahead and do a bit of that. So we're going to use our data from example 3. We're going to use our equation for the line of best fit, and we are going to do an extrapolation and an interpolation. So they want to approximate the duration, so the duration of an eruption, x, before a time of 77 minutes. So we're saying it took it 77 minutes before it erupted again. Now, it's important to pay attention to which one is x and y. We are searching for the duration x, and they gave us y. So using our equation, y is equal to 12x plus 35.1, and we were told that our time was 77, I now just need to solve for x, and in this way we'll make a prediction as to how long it had been erupting. So we'll minus a 35.1 0.1 from both sides of that. And that should give us about a 41.9 will be equal to 12x. All right, so to find x now, divide both sides by 12. And x will equal, let me go ahead and go back to Desmos. So 41.9 divided by 12 is about a 3.5. So we predict the duration of the eruption had been about 3.5 minutes, 3.5 minutes. Okay, this time predict the time, y, after an eruption lasting 50 minutes, x. So same thing, only this time they gave me the x. So y is going to equal 12 times, rather than x, we know it was 5 minutes, plus 35.1. So that's 60 plus 35.1. So y is approximately equal to 95.1. So if we did see Old Faithful erupting for 5 straight minutes, we would then predict it'll be 95.1 minutes till the next one. Now, this is a common one to talk about, correlation versus causation. Whenever you hear people talking about a recent study and they said there's been a correlation between this and this, one of the first things someone will inevitably shout is correlation is not causation. This is true, but it's only part of the story. Correlation still indicates that there's a relationship there. Now, causation means that one of your variables is causing the other to happen. So in the case of a vaccine, we expect that the rise of antibodies in the body is being caused by the vaccine put into it. One is causing the rise or fall in the other. But there can still be things that will be correlated, even though one did not cause the other. A really odd one that I've seen has been the number of firefighters in a city and the number of mailboxes in a city. There is a correlation. They are related to each other. The more mailboxes there are, the more houses there are. The more houses there are, the more firefighters there are going to be. So while mailboxes don't cause firefighters to exist, and I can't plant more mailboxes into my yard and have more firefighters exist in my neighborhood, so one is not causing the other. There is not a causation relationship. There is still a relationship, and one increases with the other. So there is correlation. So let's look at a few examples and let's see if we can't identify whether or not it's an example of correlation or causation. First, time spent exercising and the number of calories burned. Well, I would say the exercise is the cause of the calories being burned, so this would be causation. My exercising, and the longer I exercise, I cause myself to burn more calories. The number of banks and the population of a city. There is definitely correlation here. The more banks you have, it's probably a bigger city. There's not going to be 20 banks in a small town. However, in a very large city with lots of people, you need more banks to service them. So yes, there is a correlation, but having more banks doesn't cause people to have more babies. You don't increase the population of a city by building banks in it. So one does not cause the other. It is only correlation. All right, I hope this helps. Good luck.